are involved in chemical bonding. Only hydrogen beats carbon in that context. The carbon-carbon bond is extremely strong. It's about 100 times stronger than that of steel, and it's known to form about 10 million different compounds. And this is extremely flexible. And carbon, of course, is very important for technology. The reason why carbon forms so many different compounds is simply because the outermost cell, which is the 2s and 2p, are not very far from each other in energy. So if you take the electrons from the 2s to 2p, it will cost you certain amount of energy. But if it forms more chemical bonds as a result of this promotion, then it is preferable to promote the electron from 2s to 2p and form a chemical bond and therefore lower the energy. And that is the primary reason why carbon forms so many different compounds. For example, it can form sp1, sp2, or sp3. Depending upon the sp1, sp2, sp3, the structures can be linear, they can be planar, or they can be three-dimensional. But also carbon makes compounds in which there are multiple bondings present in the same compound. For example, you can have something in which you have sp1, sp2, or sp2, sp3, or sp3, sp1, or even sp1, sp2, sp3 bonding. As a matter of fact, there are about 500 plus allotropes of carbon. If you just look at organic molecules, you can make carbon in a linear chain, just primarily sp1. It can form triangles, it can form rectangles, it can form pentagons, it can form hexagons, or it can also form pentagons and hexagons. So there are a large number of the organic molecules that it can form depending upon the nature of bonding. If you look at the old phases of carbon, there are essentially three. The most common one, of course, is graphite. It is black, it is soft, it's metallic, it's cheap, and the carbon atoms in graphite are arranged in hexagons. And these are layers of graphite, layers of 6-member carbon rings. The other form of carbon, which people tell me is the material forever, is a diamond. Diamonds are forever. In this configuration, the same carbon atoms, but they're connected in tetrahedral configurations. Each carbon forms 4 chemical bonds. In graphite, it forms only 3 chemical bonds. It's not the diamond that is forever. It is actually the graphite forever. And I told this joke to Professor Sinha a couple of days ago that it is much preferable to buy your wife, your spouse, a graphite ring, because graphite are forever, and don't invest money on diamonds. And the third form of carbon is, of course, the amorphous carbon or the black soot that you get in your, in your fireplace. And
Sir,
in the last few years.
Sir, 1 second.
Yes.
Sir, just click on this height button is there. In the slide, there is a height. After this, that height you just click, then all
the height is not, you cannot see the entire slide?
No, that we can see, but the sum of the write-up is not coming. There is a, after this slide, there is a marking that height, you just click on it. No, in the back side. That middle to the slide you come. No, sir, not that way. After this nano cones, you have written the nano cones? knots are there in the middle of the
Sir,
slide.
in your slide, nanocones, where nanocones
In your
is
slide,
Yeah,
there is nanocone.
nanotubes.
In the bottom side, you see there
yeah.
height is there.
Yeah,
just below that, it's right in the mid bubble. Google is sharing your screen, then share screen, then height is written.
I do. Height, yes.
Now you yes, make the full screen.
That's it.
I see. Now you can see it?
Yeah. No, now it's clear. Good.
Okay, wonderful. So, in the last, say, 20 years or so, there have been many new forms of carbon that has appeared. And the most famous one, of course, in 1985 was what is called the fullerene or carbon 60. So 60 atoms of carbon arranged in pentagons or hexagons and make a complete or almost near perfect sphere. In 1985, the Nobel Prize was given to Smalley and the company for the discovery of the fullerene. Then, of course, came the nanotube, in which you have 6-member carbon rings that are rolled into a tube for various diameter and various chirality. For some reason unknown to me, no Nobel Prize was given to the discovery of nanotubes. But then came, of course, graphene, which is a single layer of graphite. And you can take these 6-member rings and arrange them in many different configurations. So many of the new pieces of carbon are built out of 6-member rings, with some 5-member rings that are separated from each other by, for example, hexagons. And you have nanoflex, nanotubes, graphene, graphite, all of them have the hexagon as the primary building block. As I said, C60 is one of the molecules that has pentagons and hexagons. There are 12 pentagons and 20 hexagons. And each pentagon is separate from each other by a hexagon. That is what's called the isolated pentagon rule. You cannot have 2 pentagons that form nearest neighbor, because it will introduce strain, and strain will cause instability. So therefore, the pentagons are always isolated. However, there is one particular molecule, the smallest fullerene that you can find, is carbon 20 atoms of carbon. In this 20 atoms carbon, there are several structures, and one of them is what is called a fullerene only built pentagons. And this is actually metastable. It's not the most stable form, but just like diamond is metastable and can be seen in nature, carbon 20 in a pentagonal cage is also possible to synthesize and has been indeed synthesized. But there has been no carbon structures that form an extended system only built of pentagons. And the unique properties of carbon, if you look at electrical properties, it can be metallic, insulating, or semiconducting, just the way the carbon atoms are arranged. Nothing else but only carbon. The optical properties, as I said, can be either opaque, like graphite, or transparent, like diamond. Its mechanical properties, it can be soft, as in graphite, or hard, as in diamond. The carbon can also be magnetic or not magnetic. My interest in carbon has been for the last 20 years or so, in which we look at carbon in 0 dimension, 1 dimension, 2 dimension, 3 dimension, and both stable as well as metastable forms of carbon. I will not have much time in half an hour or so that I have to talk about all the things we are doing on carbon. So I'm going to specifically mention 2 particular forms of carbon. One is called the pentagraphene, that is made only of pentagons, and a new form of carbon that we discovered last year, which we have named carbon. So there are two fundamental questions about pentagons. First of all, is it possible to form an extended framework of carbon is built only of pentagons? A typical answer will be no. You cannot make an extended structure of pentagons because pentagons will frustrate each other. The second fundamental question is it possible to prevent a system from reaching its ground state and getting confined to a metastable state? Nature always likes to find the structure in the ground state. That is why we have graphite. But it does also have diamond that is not the ground state but the metastable state. So yes, it is possible to prevent a system to get into the ground state and get stuck in a metastable state. The question is, how can we do that in a laboratory and not have nature do it for us? The reason why you cannot make pentagons in a extended frame is because when you have pentagons, there will be lot of open spaces. And therefore, that is the reason for the instability of the system. So the answer is, you cannot take regular pentagons and tile a floor. And mathematicians have been working on these pentagonal tiles for more than 100 years. And there are 15 forms, 15 types of tiles that are made only of pentagons. And I'm going to show you only one of them. You focus on this particular one that I'm showing you in the middle, and let me go to the next slide. Here, if you look at, this is an extended tile, two-dimensional tile made only of pentagons. But there is a big difference between the slide I showed you a couple of slides back and this one. Here, the pentagons are not regular. That means not all 5 sides of the pentagon are the same. Not angles of pentagon is 360 by 5. So these are irregular pentagons. And if you look at one of these 4 pentagons, say 1, 2, 3, 4, so these 4 pentagons actually make an hexagon. But this hexagon is not a regular hexagon. You have 4 long sides and 2 short sides. And this hexagon then can be used to tile a floor. So yes, you can tile a floor with only pentagons as long as 4 pentagons make a hexagon. This particular frame of pentagonal tiles is known as the Cairo pentagonal tiling. The Egyptians some 1,000 years ago knew how to actually tile a street with pentagonal tiles, and that's why it's called the Cairo pentagonal tiles. Now the question is it possible to make carbon have this kind of forms? So I am a theoretical physicist, so I do much of my work with quantum mechanics and computers, and the theory that we use is called density functional theory. It's a first principle theory, and I'm not going to go into details of this theory because it's fairly standard and may not be very relevant to all the people in the audience. So let me start by saying how actually we design this pentagonal tile. So there is a form of carbon called T12 carbon, and that is the one I'm showing in the left. If you look at the yellow portion, a middle layer. So what we did, we exfoliated this middle layer, and this middle layer actually, if you can think of, having 3 different sub-layers. You have the one in the middle and one at the top and the bottom. And here the carbon-carbon distances are different. There is one carbon-carbon that is 1.54 angstroms apart, and the other carbons are 1.56 atoms apart. So we took this particular middle layer of carbon and then we try to optimize what the structure will be if we start with an exfoliated D12 carbon. And what we get is given on the right side. And this, if you can see, is exactly what the Cairo tiling was all about. 4 irregular pentagons making a hexagon, and the hexagon can be used to make an extended periodic solid. But there is a small difference. It's not a completely flat tiling like, for example, graphene is. We put a graphene is completely flat, only one monolayer. This pentagonal tiling has 3 sublayers. The middle layer, the yellow carbon atoms, they are 4-fold coordinated. The top and the bottom carbon layers, which are black, they are 3-fold coordinated. So here is a very unique structure in which you have 2 kinds of carbon, one forming tetrahedron and one forming what it does, like, for example, in benzene. And that is where, for example, the strain is released by having adjacent pentagons. Again, if you look at the distances, there are 2 kinds of carbon atoms. The one that are making a single, single bond is about 1.55 angstrom, and the one that makes a double bond is about 1.34 angstrom. It's a buckled layer of, if you like, pentagraphene. So pentagraphene is nothing but a layered carbon structures in which the layer is actually buckled with 2 kinds of carbon, one forming 4 bonds and one forming 3 bonds. The properties of this pentagraphene is very, very different from graphene. First of all, we confirm that it's energetically, dynamically, thermally stable. If we introduce defects, it's also stable against all kinds of defects. It is a semiconductor, whether graphene is a conductor. The semiconductor with a band gap of 3.25 electron volts. They are similar to zinc oxide or gallium nitride. If you take this pentagraphene and you roll it up, you make into a tube, just like your nanotube, with one big difference. Your nanotube is either metallic or semiconducting, depends upon chirality. Pentatube is always semiconducting. It only has one kind of chirality. Pentagraphite, if I make layers of pentagraphene, I can make pentagraphite. And depending upon how these layers are stacked, you can have one particular pentagraphite that is transparent, just like your diamond, with a band gap of 5.68 eV. And another very interesting property was called the negative Poisson's ratio. Imagine you take a rubber band and you stretch a rubber band. What you'll find is that the contraction is along the perpendicular direction. So if you stretch in one direction, it will contract in the other direction. That's typically what most materials do. In this case of pentagraphite or pentagraphene, if you stretch in one direction, it will expand in the other directions as well. That's what's called the negative Poisson's ratio. Let me give you a very simple example of a material that does that. You take a piece of paper and you crumple it. And then you open it up, it expands in all directions. And there are many advantages of materials having something of that kind. Now this paper was published some 6-7 years ago. It's one of the most highly cited paper in PNAS. But pentagraphene has not been experimentally found yet. But this paper has given rise to a whole range of publications, something like about 200 papers per year on pentastructures. And they have been found, for example, in silicon nanoribbons. They have been found, for example, in peridium diselenide, and there is also penta ice, but nothing has been found in carbon. So our next target was, is it possible that we can find a way to synthesize it experimentally in the lab? So here is, for the next few minutes, let me tell you a paradigm shift in matrix design. And the design here is that we do not want to get stuck in the global minimum of the potential energy surface. We want to really prevent the system to go into stable configuration, but get stuck in a metastable state. So the conventional technique is that you always try to find the lowest energy structures. Our method is not to find the lowest structure, but a metastable structure with a large energy barrier. Then once you get in there, you get stuck, just like in the case of diamond. And this already has been used, this technique, to produce this carbon-20, which I showed you is the smallest fluorine. I started from a precursor C20H20. Similarly, another carbon structure called graphene, which has been formed with C18H6 as a starting precursor. So what we decided to do is to choose an organic molecule that has two kinds of bondings. One carbon is 4-4 coordinated and one carbon is 3-4 coordinated, just like what pentagraphene is. Then we select a supercell with certain compactness that allows the bonding between all carbon atoms once I dehydrogenate the organic molecule. And then I choose a coordinate system in which I allow all possible orientations to take place in terms of connectivity. And all these things are done using density functional theory. The molecule that we chose is called 3,3-dimethyl-1-butene. It has 6 atoms of carbon and 12 atoms of hydrogen. And you just take out all these hydrogen atoms, and that you can easily do by heating this molecule to something like 1200 degrees Celsius. Then you are left with the carbon bond. And this naked carbon bond, you have one carbon atom that is 4-4 coordinated. Now imagine that this naked carbon structures with 6 carbon atoms with 2 kinds of bondings, they react so fast with each other that they somehow preserve these 2 kinds of carbon. And it took us almost a year to develop the code in which we look at every possible combination in which the 6 carbon atoms can actually bind with each other. And then we found the minimum structure, which is given at the bottom right corner of your slide. We did find a hexagon, and it is perfectly periodic. But unlike the pentagraphene, where the hexagon was built of 4 pentagons, this structure came out to be 2 hexagons and 2 tetragons. So your 6 plus 4 is 10, 5 plus 5 is also 10. So we have similar framework, excepting that this is actually made of tetragons and hexagons and not of pentagons. And if you look at the structures, you have a carbon atom that is in red, that is 4-4 coordinated, and the one in black is 3-4 coordinated. Exactly like what pentagraphene was, but slightly different structures. As a matter of fact, if you look at one of these hexagons, and you look at the 2 carbon atoms at the center, you rotate that carbon dimer by 90 degrees and you get exactly pentagraphene. And the energy barrier to rotate is essentially negligible. So once you form this structure, one can simply transform into a pentagraphene. Again, like a pentagraphene, it is composed of 3 sub-layers. The top and bottom are 3-pole coordinated, and the middle one is 4-pole coordinated. And when you take this is what we call U graphene. The word U standing for unusual. It's unusual because if you take this particular graphene and you stagger, you put them on top of each other, a particular configuration where this comes out to be completely metallic. Here is the synthesized material made of this carbon precursor. You can actually see your face in it. And here are the symbols of my university and my colleague Joel Therian at UMass Lowell. And you can see the reflection on this carbon structure. If you look at, for example, the it's XRD pattern, it is also neither like a graphite nor like diamond. There are peaks which are very different from diamond or graphite or even amorphous carbon. As a matter of fact, we have established that it is both dynamically and thermally stable by looking at the phonons. And this particular form of carbon, which I showed is metallic, if you look at the magnetic measurements, it is also magnetic. So, depending upon how these carbon atoms are layered, they can be metallic or semiconducting, they can be magnetic or non-magnetic. So, here is a unique form of carbon that's all carbon, no defects, completely crystalline, and it is metallic as well as magnetic. Such kind of carbon has never been found. Here is a TM picture that matches very well with the TM that we actually simulate from the structure I gave you. And also you can see the XRD also match quite well. The only problem with the synthesis was that it has different forms of carbon in it. Because it was done at very high temperatures, there is some amorphous carbon, there are other forms of metastable carbon like the soda light, and we are unable to separate the magnetic carbon from these other phases that are competing in stability as well as in structure. Once that is done, we will then have a very clean sample of what I call magnetic carbon. Let me see if I can show this to show that it's actually this sample is your carbon, and we brought in a magnet to it, and you see that this will rotate as we take the magnet from one side to the other, showing that this sample is indeed magnetic. So this work, as I said, this is a very clear example between pentagraphene on the right side and what I call U-graphene on the left side. If you look at the highlighted area, you can see pentagraphene, which has these 4 pentagons inside a hexagon. And on the left side, you have U-graphene, which has 2 hexagons and 2 tetragons embedded inside also a hexagon. So I think my time is up, so I'm going to stop here. But carbon can make very interesting materials simply by changing one carbon, and one of them actually is trying to form a new kind of what I call lithium-ion batteries. But let me stop here to summarize, saying that we have developed a search algorithm using molecular precursors to find and confine a material in metastable phases. That is something that nature does not like to do. We have discovered a new carbon allotrope, which we named U-carbon because its unusual structure and properties. It is composed of equal number of 4 and 6 membered rings that contains 1/3 sp3 and 2/3 sp2. It is metallic and it is magnetic, and it also has potential applications. With that, I thank you very much, and I hope I have not bored you, and I'll be happy to answer any questions you may have.